Alright, so I just want to review for a minute or two about the antiderivative. Remember, we had little f of x and big F of x, and the integral was the antiderivative plus c. So on the left column, you'll see some little f of x's. I want you to, in the right column, find the antiderivative of those functions. I'll give you about 90 seconds to work that out. There you see my four answers. The only two here that are remotely tricky are the last two. They would both need to be rewritten. This one would need to be rewritten as 12x to the negative 3 power, and I add one to the exponent, divide the old coefficient 12 by the new exponent, negative 2. This would be rewritten as negative 10x to the negative 1/3 power. So my antiderivative is negative 15x to the 2/3 power. Today we're going to talk about the fundamental theory of calculus, part 2, for definite integrals. This is in chapter 4, section 4. So here is the fundamental theory of calculus for definite integrals. Remember from last week that a definite integral is an integral that has limits of integration, which are those little numbers that are sort of attached to that integral sign. That sort of bounds the area under the curve that I'm looking at. Now last week we did some definite integrals, but we were using geometry and Riemann sums and trapezoidal sums to find that area. And sometimes we were estimating, and sometimes using geometric integration we were finding the exact area. But obviously there has to be a way to find a definite integral, and that's where the fundamental theory of calculus comes in. The fundamental theory of calculus says that I can actually find the exact area under the curve if I take the difference between what I get when I plug b into the antiderivative subtracted by what I get when I plug a into the antiderivative. So another definition for the integral is a definite integral is big F of b minus big F of a. That is the fundamental theory of calculus. The integral between a and b of some function f of x dx is equal to big F of b minus big F of a, or the antiderivative of b minus the antiderivative of a. Starting off super simple. Alright, so let's go ahead and apply that fundamental theory of calculus. The integral between 0 and 6 of x dx. Now, because this is linear, I could do it using geometry, but now I want to use the fundamental theory of calculus part 2. So we know that this is going to be equal to big F of 6 minus big F of 3. So now we just got to figure out what big F. Big F of x is the antiderivative of x, which would be 1/2 x squared. So then this integral would be equal to 1/2 times 36 minus 1/2 times 9. Those numbers were from, well, big F of 6, When I plug 6 into my big F function, I get 1/2 times 6 squared, or 1/2 times 36. And big F of 3, that's 1/2 times 3 squared, or 1/2 times 9. So my answer would be 27/2. That's the same area I would get if I were to do this geometrically using a trapezoid and graphing it. Where this really comes into play is when I have functions that I can't integrate perfectly using geometric integration, like this parabola. Parabola, there's no shape that I can fit under there. It's not a rectangle, it's not a square, it's not a circle, so I'm going to have to use the fundamental theory of calculus. This again is going to be big F of 2 minus big F of -3. What's big F? In this case, the antiderivative of x squared is going to be equal to 1/3 x cubed. And we don't have to worry about the negatives or anything. Just plug it straight in, right? Stick to the process. The process is always going to work. So when I plug that in, I get 8/3 for big F of 2 minus -27/3, which is big F of 3. So the total area under the curve is 35/3. It works with polynomials as well. I'll give you a moment to find the antiderivative and apply the fundamental theory of calculus to the definite integral from -3 to 4 of x squared plus 2x. So using the fundamental theory of calculus, this is going to be big F of 4 minus big F of -3. Define the antiderivative. Big F of x is going to be equal to 1/3 x cubed plus 2x. So now I know that my integral would be equal to what I get when I plug 4 into that antiderivative minus what I get when I plug in -3 to this antiderivative. So that gives me 64/3 plus 8 minus the whole quantity -27/3 minus 6. So I'm going to slow down because I have all those negatives and I'm really going to take my time. So this first part, big F of 4, gives me 88/3 minus, this is -15. And on an FRQ, that's an acceptable answer. On a multiple choice, they're probably going to continue to simplify and make this 88/3 plus 45/3, and you'll probably have an answer that's 133/3. Here's another practice problem for you. Go ahead and find the antiderivative and evaluate the integral from 1 to 3 of 3 times the square root of x dx. So it's going to be equal to big F of 4 minus big F of 1. The antiderivative is 2x to the 3 halves. So I go ahead and plug that in. So this would be 2 times 4 to the 3 half power minus 2 times 1 to the 3 halves power. Now I got to do some algebra here, so I'm going to convert it into an algebra friendly form. This is equal to 2 times the square root of 4 cubed minus 2 times the square root of 1 cubed. 4 cubed is 64, the square root is 8, so this is 16 minus 2. So I evaluate that at 14. When it comes to linear absolute value functions, alright, and I want everybody to write this down, big star, draw the picture. I get a lot of people coming up to me after this test we're about to take and say, Mr. Knus, you never told us how to find the antiderivative of an absolute value function. Yeah, I know. That's the point. I need you to do this using geometry. All right? Draw the picture of this function. Draw the absolute value. Use geometry to find the area under the curve. So if I were drawing this function, when I plug in 0, I get out positive 1. When I plug in 1, I get out positive 1. And when I plug in 2, I get out 3. So we're talking about those two triangles right here. The little one has height 1 and base 1/2. The big one has height 3 and base 3 halves. So the little one has an area of 1/4 plus 9/4. So I get out 10/4 to be my area. Area under the curve is something that is always on the test in the multiple choice and the FRQ sections, and it's usually worded like this. It says find the area, sorry, there's a typo, find the area of the region bounded by the parabola y equals x squared plus 3, the line x equals 0, the line x equals 3, and the x-axis. So whenever you're doing area bounded, draw the function to help us visualize. Here's my parabola, and that's at 3. We're bounding it by this parabola, the line x equals 0, the line x equals 3, and the x-axis. So we're talking about this shape right here, which I'm outlining in blue. That's the area we're trying to find. And this is just a basic integral question. They just present it to you in a different form. You have to set up the integral. You say, okay, well, that area, that blue shape, is represented by the integral, or the area under the curve, starting at 0, starting at x equals 0, that's this point right here, going to x equals 3. It's the area under x squared plus 3. So that integral right here that we just set up gives me the area under that curve, gives me the region bounded by those 4 curves. I can pretty easily find that big F of x is equal to 1/3 x cubed plus 3x. And I can plug in, so this is going to be equal to big F of 3 minus big F of 0. Big F of 3 would give me 27/3 plus 9. Big F of 0 would give me 0. So the area bounded is equal to 18. Here's your homework for tonight. And again, the answers will be on Edmodo.